Hello there, and welcome to our journey into one of the most extraordinary cosmic scenarios imaginable. Tonight, we will explore something unprecedented, something that challenges our understanding of interstellar visitors and stellar dynamics. We are going to discover what would happen if an ancient wanderer from the depths of space met its ultimate fate in the heart of our solar system. Not just another asteroid or comet quietly passing through our neighborhood, but a true interstellar traveler on a collision course with our sun itself. We will explore the catastrophic trajectory that could bring this cosmic wanderer to its fiery end and what such an encounter might mean for our understanding of stellar physics and the delicate balance of our solar system. Before we begin this extraordinary thought experiment, I would love to know where you are joining us tonight. Perhaps you are in a quiet room, maybe lying back with your eyes closed, contemplating the vast forces at play in our universe. No matter where you are, we share this moment together, floating on our small planet through the vastness of space, protected by the very star that would become the stage for this cosmic drama. If you find these kinds of thought-provoking explorations fascinating, I would be grateful if you could subscribe or like this program. It helps this signal reach other curious minds who enjoy these journeys through the most extreme scenarios in science. Take a moment now to settle in. Let your thoughts expand to grasp the immense scales of energy and destruction we are about to explore. What if a visitor from another star, carrying within its ancient ice the secrets of distant worlds, were destined not to pass by our sun, but to plunge directly into its blazing surface? On the first day of July, in the year 2025, astronomers made a discovery that would lead us to this ultimate question. Their instruments had detected something extraordinary moving through the darkness between planets. The Atlas telescope system, perched high in the Chilean mountains, captured the faint glimmer of an object unlike any seen before in our solar neighborhood. The celestial wanderer bore the designation 3I/Atlas, marking it as the third confirmed interstellar object to grace our cosmic territory. Unlike the countless asteroids and comets born within our sun's gravitational embrace, this visitor originated from the depths of space between the stars. Scientists believe this cosmic nomad began its journey in the direction of Sagittarius, the constellation famous for housing the center of our galaxy. The exact stellar nursery that birthed this traveler remains hidden in mystery. Perhaps it formed around a star, similar to our sun, in a planetary system where ice and rock dance together in the cold outer reaches. Or maybe it emerged from the chaotic debris surrounding a young, violent star, where gravitational forces hurled objects into the void. The distance this wanderer has covered staggers the imagination. Interstellar space stretches vast and empty, with nearest neighboring stars separated by trillions upon trillions of kilometers. To traverse such distances requires not years or centuries, but potentially millions or billions of years of patient drifting through the cosmic void. During this extended voyage, the object endured temperatures only a few degrees above absolute zero, where matter itself nearly ceases to move. Evidence indicates this interstellar messenger carries the chemical signature of its alien birthplace. Observations reveal unusual concentrations of carbon dioxide frozen within its structure, along with traces of water ice, carbon monoxide, and exotic compounds like cyanide gas and metallic nickel vapor. These elements tell a story of formation processes that may differ from those that created objects in our solar system billions of years ago. Research suggests the nucleus of this cosmic visitor measures somewhere between 320 meters to 5.6 kilometers across. The uncertainty stems from the difficulty of separating the solid core from the glowing cloud of gas and dust that surrounds it. This envelope, called a coma, forms when solar radiation heats the nucleus and causes frozen materials to transform directly from ice into vapor, carrying microscopic particles with it. The trajectory of 3I/Atlas follows a hyperbolic path, meaning it will never return to our solar system once it departs. Its orbital eccentricity measures an extreme 6.141, making its path appear almost straight rather than curved. This indicates the object possesses far too much velocity to become trapped by our sun's gravitational influence. The visitor moves at approximately 58 kilometers per second relative to our star, representing one of the fastest speeds ever recorded for any object in our solar neighborhood. Astronomers have traced the object's path backward through time, confirming its interstellar origins beyond any reasonable doubt. Pre-discovery observations extend back to mid-June 2025, allowing scientists to refine their calculations of its trajectory and physical properties. Multiple observatories around the world have contributed data, creating a comprehensive picture of this unusual traveler. The discovery process itself illustrates the remarkable coordination of modern astronomical research. The Atlas network, designed primarily to detect potentially hazardous asteroids, maintains constant surveillance of the entire night sky. When unusual motion or brightness changes appear in their data, astronomers quickly alert colleagues worldwide. Within hours of the initial detection, telescopes across multiple continents began tracking the object, gathering crucial information about its size, composition, and behavior. Spectroscopic analysis has revealed fascinating details about the visitor's chemical makeup. The presence of atomic nickel vapor particularly intrigues researchers, as this suggests high-temperature processes occurred during its formation or subsequent journey. Similarly, the detection of cyanide compounds provides clues about the chemical environment of its birthplace, possibly indicating organic chemistry processes similar to those thought to have occurred in the early solar system. The object's rotation period appears to span approximately 29 hours, based on subtle brightness variations observed over several nights. This relatively slow spin suggests a stable, consolidated structure rather than a loose collection of rubble. The surface likely consists of a complex mixture of various ices interspersed with rocky and metallic components, creating a heterogeneous composition that reflects its exotic origins. Hubble Space Telescope observations have provided the sharpest images yet obtained of the interstellar visitor. These high-resolution photographs reveal fine details of the coma structure and hint at the presence of a faint tail streaming away from the nucleus. The tail forms as solar wind and radiation pressure push gas and dust particles away from the sun, creating the characteristic appearance associated with active comets. James Webb Space Telescope studies have contributed additional insights into the object's chemical composition and thermal properties. Infrared observations can penetrate the dusty coma to examine the nucleus more directly, providing estimates of temperature, size, and surface characteristics. These measurements help scientists understand how interstellar conditions have affected the object during its long journey. The timing of this discovery proves fortuitous for astronomical research. Unlike previous interstellar visitors that were detected only as they departed our solar system, 3I/ATLAS was found while still approaching its closest point to the Sun. This provides an extended observational window, allowing researchers to study how solar heating affects an object formed around another star. Current predictions indicate the visitor will reach its nearest approach to our Sun around the end of October 2025. At that time, it will pass within approximately 136 million kilometers of the solar surface, placing it roughly between the orbits of Earth and Mars. This relatively close passage will provide optimal conditions for detailed study, as increased solar heating will likely enhance the comet's activity and make its coma more prominent. The discovery of 3I/Atlas raises profound questions about the frequency of interstellar objects in our galaxy. Statistical models suggest that billions of such wanderers may be drifting through space at any given time, representing a vast population of cosmic refugees ejected from their birth systems by gravitational interactions. The vast majority remain invisible to our instruments due to their small size and great distance from any star. Some estimates suggest that the number density of interstellar objects, similar to 3I/ATLAS, may reach one object per 1,000 cubic astronomical units of space. If accurate, this implies that our solar system likely encounters such visitors on a regular basis, though most pass through undetected due to their faintness and rapid motion across the sky. The age of this interstellar traveler remains a matter of speculation and ongoing research. Based on its trajectory and estimated velocity, some scientists propose it may have been wandering through space for 3 to 11 billion years. This would make it significantly older than many objects native to our solar system, potentially preserving chemical and physical signatures from an earlier epoch in our galaxy's history. Understanding the composition and structure of interstellar objects provides valuable insights into planetary formation processes around other stars. By studying these cosmic messengers, astronomers can test theories about how planetary systems develop and evolve, comparing conditions in distant stellar neighborhoods with those that shaped our own solar system billions of years ago. The discovery also highlights the importance of continued surveillance of near-Earth space for both scientific and practical purposes. While 3I/Atlas poses no threat to Earth, maintaining awareness of objects entering our solar system helps scientists understand the local cosmic environment and provides early warning of any potentially hazardous trajectories. Ground-based telescopes continue to track the visitor as it approaches its closest solar encounter. Observations from multiple wavelengths of light reveal different aspects of its composition and behavior, creating a comprehensive scientific portrait of this interstellar messenger. Radio telescopes may eventually detect emissions from excited molecules in the coma, while X-ray observations could reveal interactions between the solar wind and the object's tenuous atmosphere. The story of 3I/Atlas represents just the beginning of a new era in astronomy. As survey telescopes become more sensitive and comprehensive, they will likely discover many more interstellar visitors, each carrying unique information about distant stellar systems and the processes that shape planetary formation throughout our galaxy. For now, this cosmic wanderer continues its ancient journey, temporarily illuminated by our sun's warmth before returning to the cold darkness between the stars. Its brief visit to our solar neighborhood provides a rare opportunity to examine matter formed around another star, offering glimpses into the diverse chemical and physical processes that occur throughout our vast galactic home. In the grand scale of cosmic time, the passage of 3I/A Telis represents merely an instant. Yet for human scientists, this fleeting encounter opens a window into the hidden universe beyond our solar system, reminding us that we are part of a much larger cosmic community where matter, energy, and information flow freely across the seemingly empty spaces between the stars. 65 million kilometers from Earth, suspended in the cold vacuum between worlds, floats a specimen unlike anything formed in our solar neighborhood. This frozen archive carries within its nucleus the preserved chemistry of another star system, locked away in crystalline lattices that have remained undisturbed for eons. The physical nature of this entity defies simple categorization. Neither purely rocky like an asteroid, nor loosely assembled like a typical comet, it represents something between these familiar classifications. Its dimensions remain elusive, hidden beneath layers of sublimating ice and dust that obscure direct measurement attempts. Current estimates place the solid core somewhere between the size of a city block and a small mountain. Beneath the shimmering envelope of gas and particulate matter lies a nucleus composed of materials, both familiar and startling. Water ice forms a significant component, as expected for any object originating in the frigid outer regions of a planetary system. However, the ratio of different ice types reveals chemical signatures that distinguish this body from local specimens. Carbon dioxide dominates the volatile composition in concentrations rarely seen among native comets. This frozen carbon dioxide, or dry ice, sublimates at higher temperatures than water ice, creating activity even at considerable distances from our sun. The abundance of this compound suggests formation in an environment where carbon dioxide could condense freely, possibly indicating different temperature and pressure conditions than those present during our solar system's birth. The presence of carbon monoxide adds another layer of complexity to the chemical portrait. This simple molecule typically requires extremely cold conditions to freeze, implying formation temperatures well below those experienced by most objects in our stellar neighborhood. Its detection hints at preservation processes that maintained these fragile compounds during the entity's lengthy transit through interstellar space. More intriguing still are the metallic components revealed through spectroscopic examination. Atomic nickel vapor streams from the nucleus as solar heating liberates embedded metallic particles. The concentration of this element suggests incorporation during the object's original formation, rather than later contamination from interstellar dust. This implies formation processes that could efficiently concentrate metals within an icy matrix. Cyanide compounds detected in the spectrum provide additional clues about the chemical environment of the object's birthplace. These organic molecules form through complex interactions between carbon, nitrogen, and other elements under specific temperature and radiation conditions. Their presence indicates that the parent system possessed the raw materials and energy sources necessary for producing organic chemistry. The internal structure likely resembles a heterogeneous mixture rather than a uniform composition. Computer models suggest alternating layers or pockets of different materials, Created as the original planetesimal, accreted various types of debris. Some regions may contain primarily water ice mixed with rocky particles, while others harbor concentrations of more volatile compounds like carbon dioxide and carbon monoxide. Density measurements provide insights into the overall porosity of the nucleus. The relatively low bulk density suggests a substantial amount of empty space between individual grains, creating a fluffy texture similar to freshly fallen snow. This porous structure would facilitate the rapid sublimation observed as the object approaches our sun, allowing internal ices to escape efficiently through interconnected pathways. The surface characteristics remain largely hidden beneath the active coma, but thermal modeling provides some constraints on composition and properties. Temperature variations across the nucleus drive differential sublimation rates, creating the asymmetric brightness patterns observed during rotation. Darker regions likely contain higher concentrations of non-volatile materials that absorb solar radiation without contributing to gas production. Crystalline structure analysis reveals information about the thermal history experienced during formation and subsequent evolution. Different ice phases form under varying temperature and pressure conditions, preserving records of the environments encountered throughout the object's existence. The specific crystal structures detected suggest relatively gentle formation processes, followed by prolonged cold storage. Isotopic ratios, measured in the sublimated gases, provide some of the most precise information about the object's origins. The relative abundances of different atomic variants can distinguish between formation scenarios and reveal details about the nuclear processes occurring in the parent star. Preliminary measurements suggest isotopic signatures that differ subtly but measurably from solar system norms. The liberation of gas and dust creates the magnificent coma that surrounds the nucleus like an ethereal atmosphere. This tenuous envelope spans thousands of kilometers in diameter, dwarfing the solid core that produces it. The coma composition reflects the nucleus chemistry, but undergoes additional transformations due to solar ultraviolet radiation and particle bombardment. Within the coma, water molecules undergo photodissociation, breaking apart into hydrogen and hydroxyl radicals that create distinctive spectral signatures. Carbon dioxide molecules similarly decompose, producing carbon monoxide and atomic oxygen that contribute to the overall emission spectrum. These secondary products provide indirect information about the nucleus composition even when the solid surface remains obscured. Dust grains entrained in the sublimating gases range in size from microscopic particles smaller than bacteria to larger fragments comparable to sand grains. The size distribution and composition of these particles reflect the mechanical properties of the nucleus surface and the efficiency of different sublimation processes. Larger grains require more vigorous gas production to achieve escape velocity from the nucleus. The rotation period of approximately 29 hours indicates a consolidated structure with sufficient internal strength to maintain coherence during rotational motion. Loose rubble piles would likely experience disruption or restructuring under the combined influences of rotation and differential heating, suggesting that binding forces within the nucleus exceed the modest gravitational attraction of such a small body. Surface features may include cliffs, valleys, and crater-like depressions created by differential erosion or impact events during the object's lengthy existence. However, the active sublimation currently occurring likely obscures or modifies these features rapidly, creating a dynamic surface that changes continuously as different regions experience solar heating. The thermal properties of the nucleus materials influence how quickly temperature changes propagate into the interior. High thermal conductivity would allow deep penetration of solar heating, while low conductivity would confine temperature changes to a thin surface layer. The observed sublimation patterns suggest intermediate thermal properties that allow heating to penetrate several centimeters or meters into the nucleus. Magnetic field measurements during the object's passage through our solar system may reveal information about metallic content and internal structure. Any significant magnetic signature would indicate substantial metal concentrations or possibly remnant magnetization acquired during formation in the magnetic environment surrounding its parent star. The mechanical strength of the nucleus determines its ability to withstand tidal stresses and thermal expansion effects. Too weak, and the object would fragment as heating creates internal pressures from sublimating ices. Too strong, and gas production would be inhibited by the inability of internal vapors to escape efficiently. The observed behavior suggests a delicate balance between structural integrity and permeability. Comparison with solar system comets reveals both similarities and differences that highlight the universal nature of certain physical processes, while emphasizing the unique aspects of interstellar formation. The basic physics of ice sublimation and dust entrainment operates identically regardless of the object's origin, but the specific chemical inventory reflects the conditions present during initial assembly. Contamination from interstellar medium during the prolonged journey between stars likely modified the surface composition to some degree. Bombardment by cosmic rays could induce chemical changes in surface materials, while accretion of interstellar dust might create a veneer of foreign material overlying the original surface. However, the bulk composition should preserve the signature of the formation environment. Laboratory analysis of collected dust samples would provide unprecedented insights into the detailed chemistry and mineralogy of materials formed around another star. Current collection technologies could potentially capture microscopic particles from the coma during the object's closest approach to Earth, though the high relative velocity poses significant technical challenges. Future missions to similar entities might employ advanced sampling techniques to obtain direct samples of nucleus material. Such specimens would represent the first tangible pieces of another star system available for detailed terrestrial analysis, opening entirely new avenues for comparative planetary science and astrobiology research. The preservation of volatile compounds over billion-year timescales demonstrates the effectiveness of cold storage in interstellar space. This natural cryogenic preservation suggests that similar objects throughout our galaxy may serve as repositories of ancient chemistry, carrying samples of stellar formation environments across vast distances and time periods. Understanding the detailed structure and composition of this entity provides crucial calibration data for models of planetary formation and evolution around other stars. Each new measurement refines our understanding of the physical and chemical processes that shape matter in the universe, extending our knowledge beyond the confines of our own stellar neighborhood. The intricate architecture revealed through careful observation reminds us that even apparently simple objects, like frozen debris possess complex internal organization reflecting their unique formation histories. This particular specimen carries within its modest dimensions a record of processes that occurred in a stellar system perhaps billions of years ago, preserved for our examination by the cold vacuum of interstellar space. As investigation continues, each new detail adds to our growing appreciation for the diversity of materials and processes that exist throughout our galaxy. This single entity serves as an ambassador from distant worlds, offering direct physical evidence of the chemistry and physics operating around other stars in our cosmic neighborhood. Scientists have identified 6 distinct layers within our Sun, each possessing unique properties that govern the flow of energy from nuclear furnace to radiant surface. This layered architecture represents one of nature's most elegant solutions to the challenge of transporting enormous amounts of energy across nearly 700,000 kilometers of stellar material. At the very center lies the core, a region of unimaginable density and temperature, where the fundamental building blocks of matter undergo transformation. Here, temperatures reach 15 million degrees Celsius, creating conditions so extreme that hydrogen nuclei overcome their natural repulsion and fuse together to form helium. This nuclear fusion process releases the energy that ultimately powers all life on Earth and drives the complex weather systems of our star. The core spans approximately 150,000 kilometers from the center, containing roughly 60% of the Sun's total mass, despite occupying less than 2% of its volume. Within this compressed realm, matter exists in a state unlike anything found elsewhere in our solar system. Electrons have been stripped from their atoms, creating a plasma so dense that a teaspoon would weigh several tons if somehow transported to Earth. Nuclear fusion proceeds through a series of carefully orchestrated steps known as the proton-proton chain reaction. 4 hydrogen nuclei combine through intermediate stages to create 1 helium nucleus, 2 positrons, 2 neutrinos, and tremendous amounts of energy. The mass difference between the initial hydrogen and final helium gets converted directly into energy according to Einstein's famous equation relating mass and energy. Each second, the Sun converts approximately 600 million tons of hydrogen into helium, releasing energy equivalent to billions of hydrogen bombs. Yet this massive energy production represents only a tiny fraction of the Sun's total hydrogen supply, ensuring stable fusion for billions of years to come. The core produces energy at a rate of nearly 400 trillion watts, though this power generation occurs throughout the entire core volume rather than at a single point. Surrounding the core extends the radiative zone, where energy begins its lengthy journey toward the surface. This region spans from approximately 150,000 to 500,000 kilometers from the center, encompassing nearly half the Sun's radius. Within the radiative zone, energy travels primarily through the absorption and re-emission of high-energy photons by the dense plasma. The journey of a single photon through the radiative zone follows a random walk path, absorbed and re-emitted countless times as it gradually works its way outward. Studies show that photons created in the core require anywhere from 10,000 to 100,000 years to traverse the radiative zone, transforming from high-energy gamma rays to lower-energy visible light through this extended process of interaction with matter. Temperature and density decrease steadily throughout the radiative zone, dropping from several million degrees at the inner boundary to approximately 2 million degrees at the outer edge. The pressure likewise diminishes as the weight of overlying material decreases with radius. These gradual changes create a smooth temperature and density gradient that supports the steady outward flow of radiant energy. Beyond the radiative zone lies the convective zone, where energy transport mechanisms change dramatically. At approximately 500,000 kilometers from the center, conditions favor convective motion rather than radiative transfer. Hot plasma rises toward the surface, while cooler material descends, creating vast circulation cells that efficiently transport energy through the remaining solar interior. The transition between radiative and convective zones occurs where the temperature gradient becomes steep enough to drive instability in the plasma. Below this boundary, radiation can transport energy efficiently enough to maintain stable layering. Above it, convective mixing becomes the dominant energy transport mechanism, creating the churning motion visible at the solar surface as granulation. Convective cells within this zone span a wide range of sizes, from small granules a few hundred kilometers across to massive supergranules, tens of thousands of kilometers in diameter. These circulation patterns create the complex surface features observed through specialized solar telescopes, including the distinctive cellular appearance of the photosphere and the dynamic evolution of solar magnetic fields. The photosphere marks the visible surface of the sun, though this boundary represents a gradual transition rather than a sharp interface. This thin layer, only a few hundred kilometers thick, produces most of the light we see from Earth. Temperatures here range from approximately 5,800 degrees Celsius, cool enough for certain atoms to retain some electrons and produce the spectral lines astronomers use to study solar composition. Observations of the photosphere reveal intricate structure created by underlying convective motions. Granules appear as bright cells surrounded by darker boundaries, where cooler plasma descends back into the interior. Individual granules typically measure 500 to 1,500 kilometers across and evolve on timescales of 8 to 20 minutes, creating a constantly changing tapestry of light and shadow. Above the photosphere lies the chromosphere, a thin atmospheric layer visible during solar eclipses as a reddish glow around the solar disk. This region extends several thousand kilometers above the visible surface, with temperatures initially decreasing with altitude before beginning to rise again in the upper chromosphere. The red coloration comes from hydrogen emission lines produced in this relatively low-density environment. The chromosphere exhibits dramatic variations in structure and temperature, with some regions reaching temperatures of 20,000 degrees Celsius, while others remain relatively cool. Spicules, narrow jets of hot gas, shoot upward from the chromosphere at speeds of several kilometers per second, carrying energy and material into the overlying corona. The corona represents the sun's outermost atmospheric layer, extending millions of kilometers into space. Despite its extremely low density, the corona reaches temperatures exceeding 1 million degrees Celsius, a phenomenon that continues to puzzle solar physicists. The heating mechanism for the corona likely involves magnetic field interactions and wave propagation, though the precise details remain subjects of active research. Coronal structure varies dramatically with the sun's 11-year magnetic cycle. During solar maximum, the corona appears relatively uniform and extended, while at solar minimum, it shows distinct streamers and holes that reflect the underlying magnetic field configuration. These variations affect the solar wind, the stream of charged particles that flows outward from the corona throughout the solar system. Magnetic fields permeate all layers of the solar interior and atmosphere, generated by the complex motions of conducting plasma within the convective zone. These fields emerge at the photosphere to create sunspots, solar flares, and coronal mass ejections that influence space weather throughout our solar system. The magnetic field structure evolves continuously as convective motions twist and reorganize field lines. The sun's rotation adds another layer of complexity to its internal structure. The equatorial regions rotate faster than the poles, with the photosphere completing one rotation in approximately 25 days at the equator compared to 35 days at the poles. This differential rotation helps generate and maintain the solar magnetic field through a process known as the solar dynamo. Internal sound waves, generated by turbulent convection, propagate throughout the solar interior and provide information about conditions deep within the sun. Heliosismology, the study of these solar oscillations, has revealed details about internal rotation rates, temperature profiles, and the location of the convective zone boundary that would otherwise remain hidden from direct observation. The sun's internal structure has remained relatively stable for approximately 4.5 billion years, with nuclear fusion rates adjusting automatically to maintain equilibrium between gravitational collapse and radiation pressure. This self-regulating mechanism ensures steady energy production despite small variations in core conditions over geological timescales. Chemical composition varies slightly throughout the solar interior due to nuclear processing in the core and mixing by convective motions. The core contains elevated helium concentrations from billions of years of fusion, while the outer convective zone maintains composition closer to the original solar nebula values. These composition gradients provide additional information about solar evolution and internal mixing processes. Understanding solar structure proves crucial for predicting how our star will respond to disturbances such as impact events. The layered architecture and internal energy transport mechanisms determine how shock waves and thermal disturbances propagate through the solar interior and ultimately affect the observable surface and atmosphere. Energy produced in the core takes thousands of years to reach the photosphere through the complex processes of absorption, re-emission, and convective transport. This means that changes in core fusion rates would not immediately affect solar luminosity, providing a natural buffer against rapid variations in energy output that could adversely affect planetary climates. The sun's internal structure represents a delicate balance between competing physical forces and energy transport mechanisms. Gravitational attraction tries to compress the star, while radiation pressure from fusion reactions pushes outward. Temperature and density gradients drive various forms of energy transport, from radiation in the interior to convection near the surface. This architectural masterpiece of plasma physics creates the stable, long-lived energy source that has nurtured the development of complex chemistry and biology throughout our solar system. The sun's layered structure ensures efficient energy production and transport, while maintaining the stability necessary for planetary habitability over billions of years. From the nuclear furnace of the core to the million-degree corona, each layer contributes essential functions to the sun's operation as our neighborhood star. This hidden architecture, invisible to casual observation, but revealed through decades of careful study, provides the framework within which any cosmic encounter must unfold. In the constellation Sagittarius, where our galactic center holds court among countless stars, a frozen relic from another world begins its final approach toward our sun. The transformation that unfolds represents one of the most dramatic encounters possible between matter and energy in our solar system. The boundary between interstellar space and solar influence remains invisible to human eyes, yet it marks a fundamental transition zone where different physical processes dominate. As our wandering ice mountain crosses into the realm of solar wind and magnetic fields, subtle changes begin that will eventually culminate in spectacular displays of celestial chemistry and physics. Solar wind particles, streaming outward from the corona at speeds approaching 400 kilometers per second, first encounter the approaching body when it lies far beyond the orbit of Neptune. These charged particles carry magnetic field lines frozen within the plasma flow, creating a dynamic environment that extends the sun's influence throughout the entire solar system and beyond into interstellar space. The initial interaction appears deceptively gentle. Solar wind pressure begins to compress and shape the thin atmosphere that already surrounds the nucleus due to sublimation of surface ices. This tenuous envelope, barely detectable by sensitive instruments, starts to develop asymmetries as the constant stream of particles creates preferential flow patterns in the escaping gases. Magnetic field interactions add complexity to this early stage of transformation. The conducting plasma surrounding the nucleus couples to the embedded solar magnetic field, creating induced currents and field compressions that affect how charged particles move through the developing coma. These electromagnetic effects influence the trajectories of ionized gas molecules and dust grains, beginning the process that will eventually create the magnificent tail visible from Earth. Radiation pressure from sunlight contributes another force, shaping the evolving atmosphere. Photons carry momentum that, while negligible for solid objects, becomes significant for microscopic dust grains and gas molecules. This pressure acts selectively, affecting smaller particles more strongly than larger ones, creating size-dependent separation effects within the coma. Temperature gradients develop across the nucleus surface as solar heating becomes more intense. With decreasing distance, the side facing the sun experiences rapid warming, while areas in shadow remain at temperatures close to absolute zero. These thermal differences drive atmospheric circulation patterns that redistribute material around the nucleus and influence the overall shape of the developing coma. Sublimation processes accelerate dramatically as surface temperatures climb above the threshold required for various ice types to transform directly from solid to vapor. Water ice begins significant sublimation at temperatures around 150 degrees below 0 Celsius, while carbon dioxide becomes active at even lower temperatures, sometimes creating activity visible from Earth while the nucleus remains far from the inner solar system. The chemistry of the expanding atmosphere becomes increasingly complex as solar ultraviolet radiation begins to affect the composition of sublimated materials. High-energy photons break apart complex molecules, creating fragments and ions that produce distinctive spectral signatures. These photodissociation processes transform the simple molecular composition of the original nucleus into a rich mixture of atoms, ions, and molecular fragments. Electron impact excitation adds another layer of chemical activity. Free electrons, accelerated by electric fields within the coma, collide with neutral atoms and molecules, raising them to excited energy states that subsequently decay by emitting characteristic wavelengths of light. These collision processes create the glowing emissions that make comet comas visible through telescopes and allow detailed spectroscopic analysis of their composition. Dust grain liberation accelerates as sublimating ices can no longer hold rocky and metallic particles firmly to the nucleus surface. These solid fragments, ranging from microscopic particles to pebble-sized chunks, become entrained in the expanding gas flow and begin their own independent trajectories, influenced by radiation pressure, gravitational attraction, and electromagnetic forces. The developing coma exhibits distinctive asymmetries that reflect both the rotation of the nucleus and the preferential heating of the sunward side. Jets of gas and dust emerge from active regions where subsurface ice deposits undergo rapid sublimation, creating fan-shaped structures that rotate with the nucleus and evolve as different surface areas experience peak solar heating throughout the rotation cycle. Ionization processes become increasingly important as the intensity of solar ultraviolet radiation and particle bombardment increases. Neutral atoms and molecules lose electrons when struck by high-energy photons or energetic particles, creating a population of charged species that respond differently to magnetic fields and electric forces than their neutral counterparts. The formation of distinct ion and neutral components within the coma marks a crucial transition in the object's evolution. These two populations interact through charge exchange reactions and collisions, but their different responses to electromagnetic forces begin to create spatial separations that will become more pronounced as the encounter with our star intensifies. Solar wind magnetic field lines drape around the obstacle presented by the expanding coma, creating a complex three-dimensional structure that channels the flow of charged particles and influences the overall shape of the interaction region. This magnetic draping effect becomes more pronounced as the coma grows larger and denser with continued sublimation. Bow shock formation may occur if the coma becomes sufficiently dense and the solar wind speed sufficiently high. This shock wave, similar to the sonic boom created by supersonic aircraft, marks the boundary where the solar wind first encounters significant resistance from the comet's atmosphere. The shock compresses and heats both the solar wind and cometary material, enhancing ionization and emission processes. Plasma instabilities begin to develop within the interaction region as different particle populations, with varying velocities and densities, attempt to achieve equilibrium. These instabilities can trigger wave generation and turbulence that further enhance mixing and energy transfer between the solar wind and cometary material. The magnetotail begins to form as solar wind magnetic field lines draped around the coma are carried downstream by the continuing plasma flow. This elongated magnetic structure extends far behind the nucleus in the anti-solar direction and provides a pathway for charged particles to escape from the interaction region, contributing to the formation of the ion tail that becomes visible as the object approaches closer to our star. Chemical differentiation becomes apparent as different molecular species respond to varying physical processes based on their mass ionization potential and molecular properties. Lighter species tend to expand more rapidly from the nucleus, while heavier molecules remain concentrated closer to the solid surface. Ionized species follow magnetic field lines, while neutral particles move primarily under the influence of radiation pressure and gas dynamics. Temporal variations in the coma structure reflect the changing solar wind conditions and the rotation of the nucleus. Solar wind speed and density fluctuate on timescales ranging from minutes to days, causing corresponding changes in the interaction processes. Meanwhile, the rotation of the nucleus creates periodic variations as different surface regions with varying ice content and topography experience solar heating. Gamma energy deposition rates increase rapidly as the object moves deeper into the region of intense solar radiation and particle bombardment. This energy input drives the sublimation processes while also heating the gas and dust within the coma to temperatures well above those of the solid nucleus surface. The resulting thermal expansion contributes to the rapid growth of the atmospheric envelope. Escape processes become more efficient as the expanding atmosphere reaches velocities approaching or exceeding the modest escape velocity of the small nucleus. Once atmospheric material achieves escape velocity, it begins independent orbital motion around the Sun, creating the extended structures that will eventually form the visible tails characteristic of active comets. The transformation of a cold, inactive interstellar body into a dynamic, evolving atmospheric system demonstrates the profound effects of stellar radiation and particle bombardment on small solar system objects. Each step in this process reflects fundamental physical and chemical principles operating under the extreme conditions present in the space environment. As this metamorphosis continues, the stage becomes set for even more dramatic changes that will occur as the object penetrates deeper into our star's realm of influence. The gentle beginning of atmospheric development will give way to increasingly violent processes as temperatures, radiation levels, and particle bombardment rates climb toward their ultimate peaks during the closest approach to our neighborhood star. The dance between matter and energy that begins in this early stage establishes patterns and structures that will persist and evolve throughout the remainder of the encounter, creating a natural laboratory for studying the fundamental processes that govern interactions between solid bodies and stellar environments throughout our galaxy. Imagine a mountain-sized block of ice accelerating to speeds that would carry it from New York to London in less than 10 seconds. This describes the final stages of our hypothetical collision as the interstellar object plunges through the outer layers of solar atmosphere toward an appointment with stellar plasma. The physics governing this descent operate on scales that challenge human comprehension. Gravitational acceleration near the Sun becomes so intense that velocity increases by hundreds of kilometers per second during the final approach. What began as a relatively sedate 58 kilometers per second at the edge of the solar system transforms into something approaching 600 kilometers per second as the object falls toward the solar surface. This acceleration follows precise mathematical laws discovered centuries ago, but never observed under such extreme conditions. The gravitational field strength increases as the square of decreasing distance, creating exponential growth in the forces acting upon the falling mass. Each kilometer closer to the solar center multiplies the attractive force, driving the object towards speeds that dwarf anything achieved by human technology. Atmospheric drag, begins to assert itself as the object penetrates the tenuous outer corona. Even though coronal density remains millions of times lower than Earth's atmosphere at sea level, the extreme velocity makes these sparse particles significant obstacles. Each collision between the object's surface and coronal plasma transfers momentum, gradually slowing the descent while converting kinetic energy into heat. The drag force increases as the square of velocity, creating a mathematical tension between accelerating gravity and decelerating atmospheric resistance. Initially, gravitational acceleration dominates completely, but as speeds climb toward relativistic fractions and atmospheric density increases with depth, drag effects begin to compete with gravitational acceleration in determining the trajectory. Heating rates during this phase reach levels that transform the object's physical state completely. Atmospheric friction deposits energy at rates measured in millions of watts per square meter of surface area. This heating intensity exceeds that experienced by spacecraft during atmospheric entry by factors of thousands, creating conditions that vaporize even the most refractory materials within seconds. The boundary between solid object and surrounding plasma becomes increasingly indistinct as surface materials undergo rapid phase transitions from ice to vapor to ionized gas. The traditional concept of a discrete surface breaks down as the object becomes surrounded by an envelope of its own vaporized material, creating a complex interaction zone where different physical processes compete for dominance. Ablation processes remove material from the object's surface at prodigious rates. Unlike the gentle sublimation experienced during the earlier stages of solar approach, ablation involves violent removal of material through direct interaction with high-velocity plasma. The rate of mass loss climbs exponentially as temperatures and plasma densities increase with continued descent. Shock wave formation marks a crucial transition in the physics of the encounter. As the object's velocity approaches and exceeds the local sound speed in the coronal plasma, it creates bow shocks that compress and heat the solar material ahead of its path. These shock waves propagate outward from the object, carrying energy and momentum into the surrounding stellar atmosphere. The object itself experiences crushing deceleration as it encounters increasingly dense layers of solar atmosphere. Forces measured in millions of times Earth's gravity attempt to slow the plunging mass, creating internal stresses that exceed the structural strength of any known material. The mechanical integrity of the nucleus cannot survive these conditions intact. Fragmentation becomes inevitable as tidal forces and atmospheric drag create differential stresses across the object. The portions facing the sun experience greater heating and drag than trailing regions, while tidal effects attempt to stretch the object in the direction of motion. These combined forces tear the original coherent mass into a stream of smaller fragments. Each fragment follows its own trajectory through the increasingly dense solar atmosphere, creating a cascade of individual shock waves and heating events. The fragmentation process continues as smaller pieces themselves experience forces that exceed their reduced structural strength, leading to progressive breakup into ever smaller components. The composition of the original nucleus plays a crucial role in determining fragmentation patterns. Rocky materials possess higher structural strength than ices, but also higher density, creating different responses to the extreme forces encountered. Metallic components may survive longer than volatile ices, but eventually succumb to the intense heating and stress. Plasma interactions become increasingly complex as the fragmented object creates multiple disturbances in the solar atmosphere. Each fragment generates its own shock system and heating zone, while the interactions between these various disturbances create turbulence and instabilities that enhance mixing and energy transfer throughout the affected region. The electromagnetic properties of the fragmented material begin to influence its behavior as temperatures climb high enough to ionize even heavy elements. Ionized fragments respond to solar magnetic fields, creating complex trajectories that differ from simple ballistic motion. These electromagnetic effects add another layer of complexity to the already intricate physics of the encounter. Radiative energy loss becomes significant as the heated fragments begin to emit copious amounts of light across all wavelengths. The energy radiated away represents a cooling mechanism that competes with continued heating from atmospheric friction and compression. This radiative cooling affects the internal temperature distribution and structural evolution of the fragments. Chemical reactions occur at rates enhanced by the extreme temperatures and pressures encountered during the descent. Normally stable compounds decompose into their constituent atoms, while the high-energy environment enables reactions that would be impossible under normal conditions. These chemical changes alter the composition and properties of the material as it descends. The timescale of the entire atmospheric transit phase measures only minutes from initial coronal contact to final surface impact. Within this brief interval, the object experiences forces, temperatures, and pressures that transform it completely from a solid interstellar wanderer into a stream of ionized plasma moving at hypersonic velocities through the solar atmosphere. Turbulent wake formation behind the fragmented object creates large-scale disturbances in the solar atmosphere that persist long after the initial passage. These wake structures carry energy and momentum throughout extended regions of the corona and chromosphere, distributing the effects of the encounter over volumes much larger than the original object itself. Energy deposition patterns depend critically on the size distribution and trajectory angles of the various fragments. Larger pieces penetrate deeper into the solar atmosphere before complete vaporization, while smaller fragments may be completely ablated in the upper corona. The angle of entry affects the path length through atmospheric layers, and thus the total energy deposition. Hydrodynamic instabilities develop at the boundaries between the hot, low-density vapor cloud surrounding each fragment and the cooler, denser solar plasma. These instabilities create mixing that enhances heat transfer and chemical reactions, while also affecting the overall shape and evolution of the disturbance region. The transition from individual fragments to a continuous stream of vapor and plasma marks the final stage of the object's existence as discrete solid matter. What began as a coherent nucleus millions of kilometers away becomes a diffuse cloud of hot gas and plasma indistinguishable from the solar atmosphere, except for its chemical composition and excess energy content. Magnetic field line distortion occurs as the conductive plasma created from the vaporized object interacts with the solar magnetic field. These interactions can trigger magnetic reconnection events that release additional energy and create complex current systems within the affected region of the solar atmosphere. The momentum carried by the original object becomes distributed throughout the solar atmosphere through the various interaction processes. Conservation of momentum requires that the Sun absorb the original orbital momentum of the interstellar visitor, though this addition proves negligible compared to the Sun's total angular momentum. As the final fragments complete their transformation into hot plasma, the stage becomes set for the climactic phase of the encounter. The energy deposited throughout the solar atmosphere by the fragmented object now begins to propagate through the stellar interior and create observable effects that will mark this cosmic collision for observers throughout the solar system. The race through fire concludes not with a single impact, but with the complete dissolution of solid matter into the stellar plasma, leaving only energy, momentum, and exotic chemical signatures to mark the passage of this interstellar visitor through our star's atmospheric layers. Throughout cosmic history, stars have endured bombardment by asteroids, comets, and debris from the space between stellar systems. Most of these encounters pass unnoticed, their effects absorbed by the immense energy reservoirs of stellar atmospheres. Yet occasionally an impact occurs with sufficient violence to create effects visible across interplanetary distances. The final approach of our fragmented interstellar visitor unfolds in mere seconds, yet those moments contain physics processes of extraordinary intensity as the stream of vaporized material and plasma plunges through the chromosphere toward the photosphere. It carries kinetic energy equivalent to millions of hydrogen bombs concentrated into a region smaller than a terrestrial continent. Contact with the photosphere triggers an explosive release of energy that dwarfs most solar flares. The hypersonic impact creates a fireball expanding at thousands of kilometers per second, instantly vaporizing solar material within a radius of several thousand kilometers. Temperatures in the impact region climb to tens of millions of degrees, approaching conditions found in stellar cores. The explosion manifests as an airburst rather than a surface crater, since no solid surface exists to contain and focus the energy release. Instead, the impact energy disperses through the solar atmosphere in all directions, creating expanding shock waves that propagate both inward toward the solar interior and outward through the chromosphere and corona. Radiation output from the impact region increases dramatically across the entire electromagnetic spectrum. X-ray emission climbs to levels normally associated with solar flares, while ultraviolet and visible light production creates a temporary brightening visible from Earth. The energy release occurs so rapidly that the affected region momentarily outshines the surrounding photosphere by factors of 10 to 100. Shock wave propagation through the solar atmosphere creates compression and heating effects that extend far beyond the immediate impact zone. These pressure waves move outward at speeds approaching the local sound velocity in the solar plasma, carrying energy and momentum into regions spanning tens of thousands of kilometers in all directions from the initial explosion. The chemical signature of the original interstellar object becomes briefly detectable in the emission spectrum of the impact fireball. Exotic elements and isotope ratios foreign to solar composition create spectral lines that stand out against the normal solar spectrum for the few minutes required for turbulent mixing to disperse these foreign materials throughout the affected atmospheric region. Magnetic field disruption accompanies the violent energy release as the explosion creates highly conductive plasma that interacts strongly with local magnetic fields. Field lines become twisted, compressed, and reconnected in complex patterns that store additional energy and create secondary instabilities throughout the impact region. Particle acceleration occurs as charged particles encounter the strong electric fields generated by the explosion and magnetic field disruption. Protons, electrons, and heavier ions gain energies reaching millions of electron volts, creating high energy particle populations that contribute to enhanced emission and heating throughout the disturbed region. The momentum transfer from the original object becomes distributed throughout thousands of cubic kilometers of solar plasma through the explosion and subsequent shockwave propagation, while the total momentum addition remains negligible compared to solar rotation. The local effects create circulation patterns and flows that persist for hours after the initial impact. Plasma instabilities develop throughout the explosion region as different temperature and density regions attempt to reach equilibrium. These instabilities create turbulence that enhances mixing and energy transport, while also generating magnetic reconnection events that release additional stored energy from twisted field configurations. Acoustic waves generated by the sudden energy release propagate deep into the solar interior, creating sunquakes similar to those observed after major solar flares. These seismic disturbances travel through the convective and radiative zones at speeds determined by the local sound velocity, carrying information about the impact throughout the solar interior. The explosion's electromagnetic pulse affects the solar wind and magnetic field throughout the local solar system. Charged particles, accelerated by the impact, create enhanced particle fluxes that modify space weather conditions near Earth and other planets for days following the event, potentially affecting satellite operations and terrestrial radio communications. Temperature equilibration between the superheated impact region and surrounding photosphere occurs through radiative cooling and convective mixing over timescales of minutes to hours. The initial temperature spike gradually decreases as energy spreads throughout larger volumes of solar material and escapes through electromagnetic radiation. Convective cells in the affected region become disrupted by the explosion, creating temporary modifications to the normal granulation patterns visible at the photosphere. These disturbances may remain detectable for several solar rotation periods as the affected material mixes with undisturbed plasma and new convective patterns establish themselves. The energy budget of the explosion includes contributions from several sources beyond the original kinetic energy of the interstellar object. Chemical energy released by reactions between exotic interstellar materials and solar plasma adds to the total energy output, while magnetic field energy stored in compressed and twisted configurations provides additional contributions as reconnection events occur. Neutrino production may occur in the most energetic regions of the explosion, where temperatures and densities reach values sufficient for nuclear reactions, while the neutrino flux would be detectable by sensitive Earth-based detectors. The total production remains orders of magnitude below that of normal solar fusion processes occurring in the core. Coronal mass ejection initiation becomes possible if the explosion occurs in a region of the photosphere where magnetic field configurations favor large-scale instabilities. The energy injection from the impact could trigger the release of magnetic energy stored in coronal loops, creating ejections of magnetized plasma that propagate throughout the solar system. The visibility of the impact from Earth depends on the location of the explosion relative to the solar disk as seen from our planet Events occurring near the solar limb create distinctive brightening and spectral anomalies that ground-based solar observatories can detect and analyze, while impacts on the far side remain hidden but may still create detectable effects in solar wind properties. Radio emission enhancement accompanies the explosion as accelerated charged particles spiral along magnetic field lines, creating synchrotron radiation detectable by radio telescopes throughout the solar system. These radio signals provide information about the magnetic field strength and particle energies in the impact region. Gravitational wave production from the explosion remains below detection thresholds for current instruments, though the rapid acceleration of large masses of solar plasma creates minute space-time distortions that propagate outward at light speed. Future gravitational wave detectors with enhanced sensitivity might detect signatures from similar events. The aftermath of the explosion reveals itself through sustained enhancement of various forms of solar activity in the affected region. Elevated X-ray emission, modified magnetic field patterns, and unusual chemical signatures may persist for days or weeks as the injected energy and exotic materials slowly disperse throughout the surrounding solar atmosphere. Comparison with observed solar flares provides context for understanding the scale and effects of the hypothetical impact. While the energy release parallels that of major flares, the rapid injection mechanism and exotic chemical composition create signatures that distinguish impact events from normal solar magnetic activity. The total energy release, while enormous by terrestrial standards, represents only a tiny fraction of the Sun's total energy output. This cosmic collision deposits approximately the same amount of energy that our star produces naturally in a few seconds, demonstrating both the violence of the event and the immense energy reserves of stellar objects. Theoretical models of stellar impacts suggest that such events may be relatively common throughout the galaxy, though most remain undetected due to the distance of other stars. The hypothetical collision provides insights into processes that may occur regularly around other stellar systems, contributing to the chemical and energy evolution of stellar atmospheres. The brief moment of maximum energy release represents the culmination of a journey that began millions of years ago in another stellar system. In those few seconds, the accumulated kinetic energy of interstellar travel becomes converted into heat, light, and motion within our Sun's atmosphere, forever altering the composition and dynamics of the affected region. As the initial explosion begins to evolve and expand, its effects propagate throughout the solar atmosphere and beyond, setting in motion a cascade of secondary processes that will create observable phenomena throughout our solar system and provide scientists with unprecedented opportunities to study the fundamental physics of stellar atmospheres under extreme conditions. The surface of our star ripples like molten honey disturbed by a dropped stone as waves of energy spread outward from the impact site in concentric circles of heat and motion. What began as a localized explosion now transforms into a vast symphony of fluid dynamics playing across tens of thousands of kilometers of stellar atmosphere. Pressure waves propagate through the photosphere at velocities approaching 10 kilometers per second, carrying the signature of the collision far beyond its initial boundaries. These acoustic disturbances compress and rarefy the solar plasma in rhythmic patterns that create temporary variations in temperature and density throughout the affected regions. The granulation pattern that normally decorates the photosphere becomes disrupted as convective cells respond to the passage of shock waves and pressure variations. Individual granules, typically persisting for 10 to 20 minutes, either collapse prematurely or expand beyond their normal boundaries as the underlying convective motions adjust to the energy input from above. Magnetic field lines threading through the impact region undergo severe distortion as the explosion pushes against their frozen-in plasma. These field lines bend, twist, and compress like elastic bands under tension, storing energy that will later release through reconnection events scattered across the disturbed area. Temperature fluctuations propagate outward in spiral patterns that reflect both the radial expansion of the initial shock wave and the rotational motion of the solar surface. Differential rotation causes disturbances originating at different latitudes to spread at slightly different rates, creating complex interference patterns in the temperature and magnetic field distributions. Convective overshoot occurs as the explosion energy penetrates deeper into the convective zone than normal surface heating would allow. This enhanced mixing brings material from depths of several thousand kilometers up to the photosphere, temporarily altering the surface composition and creating spectroscopic signatures of deeper solar layers. The chromosphere responds to the disturbance with dramatic changes in its emission characteristics. Normally invisible, except during solar eclipses, this thin atmospheric layer begins to glow brightly in specific wavelengths as shock waves heat the low-density gas and enhance collision rates between atoms and electrons. Spicules, the needle-like jets of hot gas that normally rise from the chromosphere, become enhanced and more numerous in the disturbed region. The additional energy input accelerates these vertical flows to higher velocities and extends them to greater altitudes, creating forest-like structures visible in specialized solar telescopes. Coronal loops overlying the impact site undergo rapid restructuring as magnetic field changes propagate upward from the photosphere. These graceful arcs of hot plasma, normally stable for hours or days, brighten dramatically and may erupt entirely if the field line distortion exceeds critical thresholds for magnetic instability. Solar oscillations generated by the impact propagate through the sun's interior as acoustic waves traveling at speeds determined by local temperature and density conditions. These sunquakes carry energy deep into the convective and radiative zones, creating temporary modifications to the normal pattern of pressure waves that constantly traverse the stellar interior. The frequency spectrum of these acoustic oscillations differs from normal solar vibrations, containing higher frequency components generated by the rapid energy injection of the impact. Heliosismologists studying these waves can trace their propagation paths and determine the depth to which the disturbance penetrates into the solar interior. Magnetic reconnection events multiply throughout the disturbed region as twisted and compressed field lines seek lower energy configurations. Each reconnection releases stored magnetic energy in bright flashes of X-ray and ultraviolet emission, creating a cascade of secondary explosions that extends the duration of enhanced activity. The solar wind emanating from the affected region carries modified properties compared to the normal stellar outflow. Enhanced particle densities, elevated temperatures, and unusual magnetic field configurations create a disturbed zone in the solar wind that propagates throughout the solar system over subsequent days and weeks. Coronal mass ejections may be triggered If the magnetic field disruption occurs in regions where large-scale field structures become unstable, these ejections of magnetized plasma can carry billions of tons of solar material away from the sun at speeds of hundreds of kilometers per second, creating major space weather events throughout the planetary system. Surface flows in the photosphere become modified by the momentum transfer from the explosion and its aftermath. Normally organized patterns of horizontal motion are disrupted, creating turbulent zones where material flows in complex vertical patterns that slowly decay back to normal convective organization over periods of days to weeks. The white light emission from the photosphere shows temporary brightening in the impact region as enhanced temperatures increase the thermal radiation output. This brightening appears against the normal solar disk as a brilliant patch that gradually fades as energy disperses and temperatures equilibrate with surrounding regions. Magnetic flux emergence occurs as subsurface magnetic fields become destabilized by the energy injection and buoyantly rise toward the photosphere. These emerging flux tubes create new active regions that may develop into sunspot groups if the magnetic field strength and configuration prove suitable for flux tube stabilization. Alphen waves. The special type of magnetic wave propagate outward from the disturbance carrying energy and magnetic field information throughout the corona. These waves travel at speeds determined by the magnetic field strength and plasma density, creating ripples of magnetic disturbance that extend far beyond the initial impact zone. Coronal holes, regions of open magnetic field lines that allow rapid solar wind escape, may form or be modified by the magnetic field changes induced by the impact. These holes create fast solar wind streams that affect space weather conditions throughout the inner solar system for months following their formation. The balance between radiative cooling and heating in the chromosphere and corona shifts temporarily as the additional energy input from the impact creates temperatures and densities outside the normal range for these atmospheric layers. This imbalance drives enhanced emission and modified ionization states throughout the affected volume. Plasma instabilities develop at the boundaries between disturbed and undisturbed regions as gradients in temperature, density, and magnetic field strength create conditions favorable for various types of fluid and electromagnetic instabilities. These instabilities enhance mixing and energy transport, while also generating additional wave activity. The normal cycle of granule birth, evolution and decay becomes disrupted as convective patterns adjust to the modified energy input and pressure conditions. Some granules merge to form larger structures, while others fragment into smaller cells, creating temporary departures from the typical granulation pattern. Magnetic carpet reorganization occurs as the network of small-scale magnetic elements that covers the solar surface responds to the passage of shock waves and modified convective flows. This magnetic carpet normally evolves slowly, but the impact disturbance accelerates its reorganization and may create unusual magnetic configurations. The velocity field at the photosphere shows complex patterns as acoustic waves create alternating regions of upward and downward motion across the affected area. These velocity oscillations, normally dominated by convective motions, become modulated by wave motions, with periods and amplitudes related to the impact energy and propagation characteristics. Heating of the upper photosphere and lower chromosphere creates temperature inversions where atmospheric layers normally cooler than those below become temporarily hotter. These inversions modify the formation of spectral lines and create unusual emission signatures that persist until thermal equilibrium is restored. The propagation of disturbances through the solar atmosphere demonstrates the interconnected nature of stellar physics, where events occurring at one level cascade through multiple atmospheric layers and create effects that span orders of magnitude and scale and time. Each layer responds according to its own physical characteristics, while also influencing the behavior of adjacent regions. As the immediate shock waves begin to dissipate, and the most violent phase of the disturbance concludes, the affected region settles into a new temporary equilibrium characterized by enhanced magnetic activity, modified convective patterns, and elevated emission across multiple wavelengths. This disturbed state will persist as the sun slowly returns to its normal configuration. The ripples in this sea of fire carry information about the impact throughout vast regions of the solar atmosphere, creating a natural laboratory for studying how stellar atmospheres respond to sudden energy injections, and providing insights into the complex coupling between different layers of stellar structure. From Earth, we would witness something unprecedented in recorded human history. The collision unfolds 150 million kilometers away, yet its effects reach across interplanetary space to touch our daily lives in ways both subtle and spectacular. The first hint of the cosmic drama appears in the instruments of space weather monitoring stations scattered around our planet. Satellites designed to track solar activity register unusual spikes in X-ray and ultraviolet radiation approximately 8 minutes after the collision occurs. This delay represents the time required for electromagnetic radiation to travel from Sun to Earth at light speed. Amateur radio operators notice the initial effects within hours as enhanced ionization in Earth's upper atmosphere disrupts normal radio wave propagation patterns. Frequencies that normally allow communication across continents become absorbed or scattered, while other bands experience enhanced propagation that enables unusual long-distance contacts between stations normally beyond each other's reach. The aurora phenomena begin to intensify as charged particles accelerated by the solar disturbance arrive at Earth roughly 18 hours after the impact. These particles, following magnetic field lines embedded in the solar wind, interact with our planet's magnetosphere and create enhanced versions of the northern and southern lights visible at latitudes much farther from the poles than normal. Observers in polar regions witness aurora displays of extraordinary intensity and duration. The normal green curtains of excited oxygen atoms are joined by rare red emissions from higher altitude interactions and blue-purple contributions from nitrogen excitation. These colors dance across the sky in patterns more complex and vibrant than typical aurora, creating natural light shows visible even in areas with significant light pollution. The magnetic field disturbances accompanying the enhanced particle bombardment effect technological systems throughout Earth's magnetosphere. Global positioning satellites experience temporary accuracy degradation as their precise timing signals become contaminated by increased radiation levels and ionospheric irregularities. Power grids in high-latitude regions face stress from geomagnetically induced currents created by the rapidly changing magnetic field environment. Utility companies activate protective protocols developed for severe space weather events, potentially creating temporary power interruptions in affected areas while grid stability is maintained. Astronauts aboard the International Space Station and other orbital facilities receive increased radiation exposure, requiring them to shelter in protected areas of their spacecraft. Mission controllers postpone planned spacewalks and adjust orbital activities to minimize crew exposure during the peak phases of the particle bombardment. Commercial aviation routes over polar regions require modification as enhanced radiation levels make these normally efficient flight paths temporarily hazardous for both passengers and crew. Airlines reroute flights to lower latitudes, adding flight time and fuel consumption, but ensuring safety during the elevated radiation environment. The visual appearance of our sun changes subtly when viewed through proper solar filters or specialized telescopes. Professional and amateur solar observers detect the bright region where the impact occurred, appearing as an enhanced active area that persists for several days as the disturbed solar atmosphere slowly returns to normal. Satellite communications experience intermittent disruptions as enhanced particle fluxes and ionospheric disturbances interfere with radio signals passing between ground stations and orbital relay satellites. Mobile phone networks, internet services, and broadcast television may show temporary degradation in regions dependent on satellite links. Weather satellites provide dramatic images of Earth's atmospheric response to the increased energy input. Enhanced aurora activity appears as glowing regions in ultraviolet and X-ray images, while atmospheric heating at high altitudes creates temperature and density changes detectable by sensitive meteorological instruments. The particle detectors aboard research spacecraft throughout the solar system register the passage of the enhanced particle flux as it propagates outward from the sun. These measurements provide valuable data about the propagation of solar energetic particle events and their effects on the interplanetary environment. Radio telescopes around the world detect enhanced emissions from the disturbed solar atmosphere. These radio signals, generated by accelerated charged particles spiraling along magnetic field lines, provide information about the magnetic field strength and particle energies in the impact region that complements observations at other wavelengths. Solar observatories capture spectacular images and spectra of the impact aftermath. The enhanced emission in X-rays, ultraviolet, and visible light creates photographic opportunities unlike any previous solar observations. Spectroscopic analysis reveals the exotic chemical composition of the original interstellar visitor, mixed temporarily with normal solar material. Amateur astronomers, with proper equipment, witness the temporary brightening of the affected solar region. This enhancement, while requiring specialized filters and telescopes for safe observation, provides visible confirmation of the impact effects for ground-based observers throughout the daylight hemisphere. The timing of the event relative to Earth's rotation determines which regions experience the most dramatic effects. Areas facing the sun during peak emission phases witness the strongest electromagnetic and particle bombardment, while regions on the night side experience delayed effects as particles follow complex trajectories through the magnetosphere. Scientific research facilities dedicated to solar terrestrial physics experience unprecedented data collection opportunities. The combination of enhanced solar activity, modified space weather conditions, and unusual chemical signatures provides researchers with natural laboratory conditions impossible to replicate artificially. Educational institutions around the world use the event as a teaching opportunity, demonstrating the connections between solar physics, space weather, and terrestrial technology. Students can observe real-time effects of solar activity on Earth's technological infrastructure and atmospheric phenomena. The event creates temporary modifications to Earth's radiation belts as enhanced particle fluxes become trapped in our planet's magnetic field. These particles, spiraling back and forth between magnetic mirror points in the northern and southern hemispheres, create elevated radiation levels that persist for weeks following the initial solar disturbance. Climate research instruments detect subtle changes in atmospheric chemistry as enhanced ultraviolet radiation from the solar impact region affects ozone production and destruction processes in Earth's stratosphere. While these changes prove minor and temporary, they provide insights into the complex relationships between solar variability and atmospheric chemistry. Ocean surface temperatures show minimal direct effects from the solar impact, as the thermal inertia of large water masses prevents rapid response to short-term changes in solar output. However, sensitive satellite measurements may detect tiny variations in sea surface temperatures in regions experiencing peak radiation enhancement. The psychological impact on human populations varies widely depending on media coverage and public understanding of the phenomenon. While the actual effects on daily life remain modest for most people, the knowledge that Earth has been touched by an interstellar collision creates a sense of cosmic connection and vulnerability that resonates throughout various cultures. Emergency management agencies activate monitoring protocols developed for space weather events, tracking the progression of effects through Earth's technological infrastructure, and ensuring that critical systems maintain functionality during the enhanced radiation environment. These preparations demonstrate the growing recognition of space weather as a significant factor in modern technological society. The event provides validation for space weather prediction models and demonstrates the importance of continued investment in solar monitoring and atmospheric research. The ability to forecast and prepare for such events proves crucial for maintaining the technological infrastructure upon which modern civilization depends. Agricultural systems experience minimal direct effects, though researchers monitor crop growth patterns in high-latitude regions where enhanced radiation and atmospheric chemistry changes might influence plant development. The short duration of the event limits any significant biological impacts. The recovery period extends over several weeks as Earth's magnetosphere and ionosphere gradually return to normal conditions. Enhanced aurora activity slowly diminishes, radio propagation patterns stabilize, and satellite operations return to standard protocols as the effects of the interstellar collision fade into memory. Documentation of the event creates a comprehensive record of how Earth responds to extreme space weather conditions. This information proves invaluable for improving prediction models, developing better protective technologies, and preparing for future encounters with interstellar objects or severe solar storms. The collision serves as a reminder of Earth's position within the dynamic environment of our solar system, where events occurring millions of kilometers away can influence everything from radio communications to the beauty of polar skies. This cosmic connection highlights both our planet's vulnerability and its resilience in the face of celestial phenomena. As the immediate effects subside and normal conditions return, the memory of strange skies and disrupted technologies lingers as a testament to the interconnected nature of solar system dynamics and the ongoing influence of cosmic events on our terrestrial existence. Hidden within the light of this collision lies information more precious than any treasure, waiting to be decoded by scientists who have spent lifetimes learning to read the stories that atoms tell through their electromagnetic emissions. Each wavelength carries clues about processes that occurred billions of years ago in stellar systems we can never hope to visit. Spectroscopic analysis begins immediately as ground-based observatories and space telescopes point their instruments toward the disturbed region of our star. The light collected during those crucial minutes of peak emission contains absorption and emission lines that serve as fingerprints for every element present in the original interstellar object. Isotope ratios revealed in the spectrum provide the most direct evidence of the object's alien origin. The relative abundances of different forms of oxygen, carbon, nitrogen, and silicon differ subtly but measurably from solar system values, indicating nucleosynthesis processes that occurred under different conditions in another stellar environment. The detection of unusual nitrogen isotope ratios suggest formation in a region where stellar winds from massive stars contributed significantly to the local chemistry. These ratios can only be created by specific nuclear processes occurring in stars much more massive than our Sun, providing clues about the stellar population present in the object's birth region. Oxygen isotope signatures point toward formation in an environment enriched by supernova explosions. The characteristic pattern of oxygen 16, 17, and 18 isotopes matches theoretical predictions for material processed through explosive nucleosynthesis, indicating that supernova influenced the chemistry of the original planetary system. Carbon isotope measurements reveal information about the carbon sources available during the object's formation. The ratio of carbon-12 to carbon-13 provides insights into whether organic molecules formed through processes similar to those that created carbon compounds in our own solar system or through alternative chemical pathways. Trace element detection offers glimpses into the metallicity of the parent stellar system. Elements heavier than hydrogen and helium were produced in previous generations of stars and distributed through interstellar space by stellar winds and supernovae. The abundance pattern of these metals provides information about the galactic chemical evolution in the object's birth region. Noble gas isotope ratios, particularly those of neon, argon, krypton, and xenon, carry signatures of different stellar nucleosynthesis processes. These chemically inert elements remain largely unchanged since their formation, making them excellent tracers of the nuclear processes that created the original planetary materials. Presolar grain identification within the spectrum may reveal the presence of microscopic particles that predate the formation of our solar system. These ancient grains, formed in the atmospheres of dying stars, carry isotopic signatures so extreme that they stand out clearly against the background of normal solar material. Organic molecule detection provides information about the carbon chemistry present in the original interstellar object. Complex hydrocarbons, alcohols, acids, and even amino acid precursors may have been present in the nucleus, offering insights into the organic chemistry occurring in other planetary systems. Water isotope measurements reveal the deuterium to hydrogen ratio, which varies depending on the temperature and radiation environment during ice formation. This ratio provides information about the thermal history of the object and the conditions present in its original stellar neighborhood. Magnetic field strength estimates derived from Zeeman effect measurements in spectral lines indicate the magnetic environment experienced by the object during its formation. Strong magnetic fields associated with young stellar objects create different isotope patterns than weaker fields present around older, more evolved stars. Chemical abundance patterns for elements ranging from lithium to uranium provide comprehensive fingerprints of the nucleosynthesis processes that created the object's constituent materials. Each element forms through specific nuclear reactions occurring at different stages of stellar evolution, creating abundance signatures that reveal the stellar masses and evolutionary phases involved. Molecular complexity analysis reveals the degree of chemical processing that occurred during the object's journey through interstellar space. Cosmic ray bombardment and ultraviolet radiation from distant stars can create or destroy complex molecules, leaving signatures of the interstellar conditions experienced during its lengthy transit. Crystal structure information obtained from X-ray emission lines indicates the physical conditions present during ice formation in the original planetary system. Different crystal structures form at different temperatures and pressures, preserving records of the thermal and mechanical environment in the parent system's outer regions. Contamination assessment distinguishes between materials native to the original object and substances acquired during its journey through interstellar space. The interstellar medium contains trace amounts of gas and dust that could modify surface composition over million-year timescales. Redshift measurements of emission lines might reveal information about the object's velocity relative to its stellar birthplace. If the parent star system possessed significant radial velocity relative to our solar system, this motion would be preserved in the spectral characteristics of material ejected from that system. Chemical gradient analysis across the impact region reveals how different materials from various depths within the original nucleus mixed during the collision. The outer layers, more heavily processed by cosmic ray bombardment, show different composition from interior materials preserved in pristine condition. Temporal evolution of the spectrum during the minutes following impact shows how different elements and compounds behave under extreme temperature and pressure conditions. Some materials vaporize immediately, while others require more time and energy to decompose into atomic constituents. Comparison with solar composition highlights the similarities and differences between stellar systems, providing insights into the universality of planetary formation processes. Elements present in similar ratios suggest similar formation environments, while major differences indicate alternative evolutionary pathways. Statistical analysis of multiple emission lines allows scientists to separate signals from different sources within the impact region. Solar material heated by the explosion produces different spectral signatures than vaporized interstellar material, enabling researchers to isolate the foreign components. Laboratory correlation involves comparing observed spectra with controlled experiments that recreate extreme temperature and pressure conditions. These laboratory studies help interpret the observed emissions and determine the physical conditions present during various phases of the impact and its aftermath. Atmospheric modeling uses the spectroscopic data to reconstruct the structure and composition of the original interstellar object. By working backward from the observed emission patterns, scientists can infer the distribution of different materials within the nucleus before impact. Galactic chemical evolution constraints emerge from the detailed composition analysis. The abundance patterns observed provide data points for models of how chemical elements are created distributed, and recycled throughout our galaxy over billions of years of stellar evolution. Exoplanet atmosphere analogies arise, and scientists recognize that the vaporized interstellar material may resemble the atmospheric composition of rocky planets orbiting other stars. This provides rare direct evidence of planetary material compositions beyond our solar system. Dating techniques based on radioactive decay products may reveal age estimates for the original object. Long-lived isotopes created during nucleosynthesis decay at known rates, providing chronometers that reveal when the parent stellar system formed its planetary materials. Stellar wind signatures preserved in isotope ratios indicate the mass and evolutionary state of the parent star when the object formed. Different types of stellar winds produce characteristic isotopic signatures that remain detectable even after billions of years of interstellar travel. Supernova distance estimates emerge from analysis of specific isotope ratios that are created only by explosive nucleosynthesis. The relative abundances of these isotopes indicate how close the original planetary system was to supernova explosions during its formation epoch. Binary star system indicators may be present if the object formed in a system with multiple stellar components. The complex gravitational and radiation environments around binary stars create distinctive chemical and isotopic signatures in planetary materials. The spectroscopic detective work continues for months following the collision as scientists analyze data from multiple instruments and wavelength ranges. Each new measurement adds pieces to the puzzle of understanding where this interstellar visitor originated and what conditions shaped its formation billions of years ago. The wealth of information extracted from those brief moments of impact light represents one of the most detailed analyses ever possible of material formed around another star. This treasure trove of data advances our understanding of stellar and planetary formation processes throughout our galaxy while providing direct physical evidence of the cosmic processes that create and distribute the chemical elements essential for life. Slowly, the disturbance fades like ripples on a cosmic pond as our star begins the patient work of healing itself from this brief but intense encounter with matter born beneath alien suns. The processes of recovery unfold across timescales ranging from hours to years, demonstrating the remarkable resilience of stellar systems in the face of cosmic disruption. The initial shock waves that propagated through the solar atmosphere gradually lose energy as they spread across ever larger volumes of stellar material. What began as violent compression waves carrying enormous energy becomes gentle pressure variations that eventually merge with the background noise of normal solar convection and magnetic activity. Thermal equilibration proceeds through the natural processes of radiation and convection that govern energy transport throughout stellar atmospheres. The superheated plasma created by the impact slowly cools toward normal photospheric temperatures as energy disperses through electromagnetic radiation and mixing with surrounding material at lower temperatures. Magnetic field relaxation occurs as the twisted and compressed field lines seek lower energy configurations through reconnection events and gradual unwinding. The magnetic energy stored during the initial disturbance releases slowly through a series of smaller flares and heating events that extend the recovery period over several solar rotation cycles. Convective cell reformation begins as the disrupted granulation pattern gradually reorganizes into the familiar cellular structure characteristic of normal solar surface activity. New granules form where old ones were destroyed, while surviving cells slowly return to their typical sizes and lifetimes as the energy input from the impact dissipates. The exotic chemical signatures introduced by the interstellar visitor become increasingly diluted as turbulent mixing distributes the foreign materials throughout larger volumes of solar atmosphere. Within weeks, the unusual isotope ratios and trace element concentrations fade below detection thresholds as they become homogenized with normal solar composition. Coronal restructuring proceeds as magnetic field changes propagate upward from the photosphere and create new configurations of coronal loops and streamers. Some magnetic structures collapse and reform entirely, while others gradually evolve back toward configurations similar to those present before the impact. Solar wind modifications persist for weeks as the enhanced particle flux and modified magnetic field geometry propagate throughout the solar system. Spacecraft throughout our planetary neighborhood continue to detect the passage of this disturbed solar wind long after the initial impact effects have faded at the sun itself. The enhanced particle populations trapped in Earth's radiation belts slowly decay through atmospheric interactions and charge exchange processes. What began as a dramatic enhancement in trapped particle fluxes gradually diminishes as the additional particles either escape to interplanetary space or are absorbed by the upper atmosphere. Aurora activity returns to normal levels as the supply of energetic particles from the solar disturbance diminishes and Earth's magnetosphere recovers its typical configuration. The spectacular displays visible at low latitudes during the peak of the event fade back to normal polar region activity patterns. Atmospheric chemistry effects in Earth's stratosphere reach equilibrium as enhanced ultraviolet radiation levels return to normal and ozone production and destruction processes resume their typical balance. The temporary modifications to atmospheric composition prove minor and short-lived compared to natural variations. Solar oscillation patterns gradually return to their normal spectrum as the acoustic waves generated by the impact disperse throughout the solar interior and lose coherence through damping and interference effects. The sunquake signatures fade into the background of continuous stellar vibrations. Magnetic flux evolution continues for months as the subsurface magnetic fields, destabilized by the impact, slowly reorganize and either emerge at the photosphere to form new active regions or dissipate through magnetic diffusion processes in the convective zone. Temperature profiles in the affected atmospheric layers slowly flatten as radiative cooling and convective mixing eliminate the hot spots created by the initial energy deposition. The process occurs more rapidly in the lower, denser atmospheric layers and more slowly in the tenuous upper corona. Pressure equilibration eliminates the compression and rarefaction zones created by shock wave propagation. The normal hydrostatic balance of the solar atmosphere reasserts itself as pressure gradients adjust to support the overlying atmospheric layers against gravitational attraction. Spectroscopic signatures of the impact fade gradually as emission enhancements return to normal levels and the unusual chemical compositions become too diluted to detect. Solar spectra slowly return to typical patterns, dominated by normal photospheric emission from hydrogen, helium, and metals at standard solar abundances. particle acceleration sites created by magnetic reconnection events in the disturbed region slowly diminish in number and intensity as magnetic field configurations stabilize. The enhanced high-energy particle production that characterized the impact aftermath gradually returns to background levels typical of quiet solar conditions. Coronal mass ejection triggering potential decreases as the magnetic energy stored in compressed and twisted field configurations dissipates through reconnection events and field relaxation processes. The probability of large-scale eruptions returns to levels determined by normal solar cycle dynamics. Space weather impacts throughout the solar system diminish as the enhanced particle fluxes, magnetic field disturbances, and electromagnetic emissions return to typical solar minimum or maximum levels, depending on the phase of the 11-year solar activity cycle. The long-term evolution of the affected region may show subtle differences from normal solar surface activity for months or even years following the impact. These residual effects could include modified magnetic field patterns, slightly altered convective flow structures, or enhanced probability of active region formation. Statistical analysis of solar activity following the impact reveals whether the event created any lasting changes to normal solar behavior patterns. Researchers compare post-impact activity levels, magnetic field distributions, and eruption frequencies to long-term baselines to identify persistent effects. Theoretical models of the recovery process provide predictions for how long various effects should persist and at what rates they should decay. Comparison between observations and theoretical expectations helps validate our understanding of solar physics and stellar atmospheric dynamics under extreme conditions. The memory of the impact may persist in subtle ways that only become apparent through careful long-term monitoring. Changes to magnetic field topology, modifications to convective pattern organization, or alterations in the distribution of subsurface magnetic flux could influence solar behavior for years following the initial event. Seasonal variations in space weather effects gradually return to patterns determined by Earth's orbital motion and the tilted solar rotation axis, rather than being dominated by the impact aftermath. The natural cycles of solar-terrestrial interaction reassert themselves as the artificial perturbation fades. Comparative studies with similar events, either observed impacts or major solar flares, help place the recovery timeline in context and improve understanding of how stellar atmospheres respond to sudden energy injections. Each such event adds to our database of stellar behavior under extreme conditions. The restoration of normal solar conditions demonstrates the fundamental stability of stellar systems and their ability to absorb significant perturbations without permanent damage. This resilience reflects the enormous energy reserves and self-regulating mechanisms that maintain stellar structure over billion-year timescales. Monitoring instrumentation continues to search for subtle long-term effects as the sun settles back into its normal pattern of activity. Some changes may prove so minor that they remain detectable only through sophisticated analysis techniques applied to years of accumulated data. The complete cycle from initial impact through full recovery illustrates the timescales over which different physical processes operate in stellar environments. Electromagnetic phenomena occur in seconds. Thermal equilibration requires minutes to hours. Magnetic field evolution spans days to months, and chemical mixing processes may continue for years. As the final echoes of the collision fade into the background noise of normal solar variability, our star returns to its role as a stable, long-lived energy source for planetary climate and the complex web of life throughout the solar system. The brief cosmic encounter becomes part of solar history, remembered only in scientific databases, and the memories of those who witnessed this rare glimpse into the dynamic nature of stellar physics. The recovery demonstrates that even dramatic cosmic collisions represent merely temporary perturbations in the vast cycles of stellar evolution, absorbed and dissipated by processes that have operated unchanged throughout the billions of years since our sun first ignited its nuclear furnace and began its steady journey through galactic space. Across our galaxy, beneath the light of 400 billion stars, similar dramas unfold with frequencies that would astonish astronomers if they could witness them all. The collision we have imagined represents just one instance of a cosmic process that has shaped stellar atmospheres and planetary environments throughout the Milky Way for billions of years. Statistical models suggest that interstellar objects impact stars throughout our galaxy at rates approaching one event per star system every few million years. With the vast number of stars in the galactic disk and halo, this translates to thousands of such collisions occurring somewhere in our galaxy every single day, creating a continuous background of stellar disturbances invisible to our current observational capabilities. The variety of impacting objects spans an enormous range of sizes, compositions, and velocities. Some stellar encounters involve kilometer-sized comets, similar to our hypothetical 3I/Atlas collision, while others feature asteroid-scale rocky bodies, or even larger objects approaching planetesimal dimensions. The most dramatic events occur when entire planetary cores, ejected from disrupted stellar systems, collide with foreign stars. Different stellar types respond to impacts in markedly different ways. Massive hot stars with extensive convective atmospheres may barely register the effects of small interstellar collisions, while red dwarf stars with their compact, dense structures could experience proportionally larger disturbances from the same impacting mass. White dwarf stars represent extreme cases where even modest impacts can trigger nova explosions. Young stellar objects, surrounded by protoplanetary disks, experience particularly complex interactions when interstellar debris enters their systems. The impact may occur within the dusty disk rather than directly on the stellar surface, creating spectacular disruption of planetary formation processes and redistributing material throughout the developing system. Binary star systems add layers of complexity to interstellar impact scenarios. Objects approaching such systems navigate gravitational fields dominated by two or more stellar components, leading to complex orbital trajectories that may result in multiple stellar encounters or capture into highly eccentric orbits around one system member. Stellar metallicity influences both the frequency and effects of interstellar impacts. Stars formed from gas clouds, enriched by previous generations of stellar evolution, possess different atmospheric compositions that respond differently to foreign material injection. Population-A stars like our Sun show different impact signatures than metal-poor population-to stars formed in the early galaxy. The galactic environment affects interstellar object populations and their collision rates with stars. Regions near the galactic center experience higher stellar densities and more frequent gravitational interactions that eject planetary material, while spiral arm regions see enhanced rates due to star formation activity in the presence of massive stellar associations. Observational evidence for stellar impacts remains challenging to obtain. Given current technological limitations, most events occur too far away and too briefly to detect with existing instruments. However, some stellar flares and nova events may actually represent impact signatures rather than purely magnetic or thermonuclear phenomena. Variable stars showing unusual brightness fluctuations or spectroscopic anomalies might provide indirect evidence of impact events. The temporary introduction of exotic chemical species could create spectral signatures that distinguish impact-related brightening from other causes of stellar variability. Exoplanet transit observations occasionally reveal unexplained dimming events that could represent debris clouds created by interstellar impacts on the host stars. These transient dimming episodes, lasting hours to days, match theoretical predictions for dust and gas clouds produced by stellar collision events. Space-based observatories, with all-sky monitoring capabilities, represent our best hope for detecting interstellar impact events in real time. Missions designed to search for transient phenomena might identify the characteristic light curves and spectral evolution associated with stellar collisions throughout our local galactic neighborhood. Theoretical modeling of galactic impact rates requires understanding the population dynamics of interstellar objects, stellar velocities, and gravitational focusing effects. Monte Carlo simulations suggest that most stars will experience at least one significant impact during their main sequence lifetimes, though detection remains challenging. The chemical evolution of stellar atmospheres receives contributions from impact events throughout galactic history, while individual collisions produce only localized and temporary compositional changes. The cumulative effect of millions of impacts over billions of years may influence the overall metallicity distribution among stellar populations. Planetary atmosphere evolution around other stars could be influenced by stellar impact events that modify the radiation and particle environment. Enhanced stellar activity following impacts might drive atmospheric escape processes or create complex photochemical reactions in planetary atmospheres throughout the affected stellar system. Astrobiology implications arise when considering how stellar impacts might affect the development of life around other stars. Temporary increases in harmful radiation could disrupt biological processes, while the introduction of exotic chemical species might provide new raw materials for prebiotic chemistry. Stellar wind modifications following impact events could alter the space weather environment throughout entire planetary systems for extended periods. Planets orbiting within a few astronomical units of impact-affected stars would experience enhanced particle bombardment that could strip atmospheric components or enhance aurora phenomena. Gravitational wave signatures from stellar impacts remain below current detection thresholds, but might become observable with future, more sensitive instruments. The rapid acceleration of stellar plasma during impact events creates weak gravitational wave emissions that could provide information about collision dynamics. Comparative planetology benefits from understanding impact processes around different stellar types. The formation and evolution of planetary systems depends partly on the impact history of their host stars, which affects the radiation and chemical environment during critical early phases of planetary development. Long-term stellar evolution may be subtly influenced by cumulative impact effects over billion-year timescales. While individual collisions create only temporary disturbances, the accumulated effects of many impacts could modify stellar rotation rates, magnetic field generation, or convective zone properties. The search for extraterrestrial intelligence could be affected by stellar impact events that temporarily disrupt technological civilizations through enhanced radiation or electromagnetic interference. Such events might create gaps in observable technosignatures or modify the development patterns of advanced civilizations. Galactic archaeology uses stellar chemical abundances to trace the history of star formation and chemical evolution throughout our galaxy. Impact events contribute to this chemical mixing process, though separating impact signatures from other nucleosynthesis sources remains challenging with current analytical techniques. Future observational programs dedicated to stellar impact detection could revolutionize our understanding of interstellar medium dynamics, stellar atmosphere physics, and planetary system evolution. Coordinated monitoring campaigns using multiple wavelength ranges might identify impact events and track their evolution in real time. The frequency of interstellar impacts provides constraints on the population of free-floating objects in our galaxy. Detection rates of stellar collision events could help determine whether interstellar space contains vast numbers of ejected planets, comets, and asteroids that represent a significant component of galactic dark matter. Stellar seismology might detect the acoustic signatures of impact events in nearby stars, similar to heliosismology studies of our own sun. The characteristic oscillation patterns created by sudden energy injection could provide information about stellar internal structure and impact energetics. Laboratory astrophysics experiments attempt to recreate the extreme conditions present during stellar impacts, providing validation for theoretical models and helping interpret observational data. High-energy laser facilities and particle accelerators can simulate some aspects of the collision physics under controlled conditions. Cultural and philosophical implications arise from recognizing that cosmic collisions regularly affect stellar systems throughout our galaxy. This perspective emphasizes the dynamic, interconnected nature of galactic evolution and the ongoing exchange of matter and energy between stellar systems. The cosmic perspective reveals that our hypothetical collision between 3I/Atlas and our Sun represents just one thread in a vast tapestry of interactions that have shaped the chemical and physical evolution of our galaxy throughout cosmic history. Each impact event contributes to the ongoing cycle of matter and energy exchange that connects stellar systems across hundreds of thousands of light years. Understanding these galactic scale processes enhances our appreciation for the complex web of relationships that link stellar evolution, planetary formation, and the chemical enrichment of interstellar space. Our sun and solar system exist within this dynamic environment, occasionally touched by messengers from distant stellar neighborhoods. The fires that burn around other stars experience similar encounters with wandering debris, each collision adding its own chapter to the ongoing story of galactic evolution and the cosmic cycles that govern the formation, evolution, and ultimate fate of stellar systems throughout our vast island universe. In the grand choreography of space and time, where matter and energy perform their eternal ballet across the cosmos, our imagined collision represents but a single step in a dance that began with the first stars and will continue until the universe grows cold and dark. The interstellar wanderer has completed its journey, transformed from solid ice to stellar plasma, yet the greater dance continues unchanged. The patterns that governed this cosmic encounter operate at scales both intimate and infinite. The same gravitational forces that guided our interstellar visitor through its final plunge also orchestrate the motions of galaxies separated by millions of light years. The nuclear processes that heat stellar cores operate according to quantum mechanical principles that govern the behavior of individual atoms. Time reveals different aspects of the cosmic choreography depending on the scale of observation. From our human perspective, the collision unfolds as a dramatic event spanning mere hours from initial atmospheric contact to final energy dissipation. Yet from the viewpoint of stellar evolution, this encounter represents an instantaneous fluctuation in processes that continue steadily for billions of years. The conservation laws that physics has discovered operate with perfect consistency throughout this grand performance. Energy changes form but never disappears, transforming from kinetic motion to heat, from heat to light, from light to the gentle warming of planetary surfaces billions of kilometers away. Mass and momentum flow from one reservoir to another, but remain accountable in the cosmic bookkeeping. Entropy increases as ordered motion becomes random thermal energy, as organized chemical structures decompose into individual atoms, as concentrated energy disperses throughout ever larger volumes of space. This universal tendency toward disorder drives the evolution of stars, the formation of planetary systems, and the chemical processes that make life possible. The cycles of stellar birth, evolution, and death create the elements necessary for rocky planets and biological chemistry. Massive stars synthesize carbon, oxygen, silicon, and iron in their nuclear furnaces, then distribute these elements throughout interstellar space through stellar winds and supernova explosions. Subsequent generations of stars inherit this chemical legacy and continue the enrichment process. Planetary formation occurs as gravitational attraction assembles dust and gas into larger structures, creating the environments where complex chemistry can develop. Some planets retain their original compositions, while others undergo modification through impacts, atmospheric evolution, and internal differentiation processes that concentrate different materials in distinct layers. Life emerges where conditions permit the organization of simple chemicals into self-replicating systems capable of evolution and increasing complexity. The energy sources that power biological processes ultimately derive from stellar nuclear fusion, whether directly through photosynthesis or indirectly through the geological processes that concentrate chemical energy in planetary interiors. Intelligence develops as biological evolution produces nervous systems capable of processing information about environmental conditions and making decisions based on that information. The emergence of consciousness represents a new phase in cosmic evolution where the universe becomes capable of contemplating its own existence and behavior. Technology extends the reach of intelligence beyond biological limitations, creating tools for observing distant galaxies, detecting subtle radiation from ancient cosmic events, and modeling the complex physics that governs stellar and planetary evolution. Through technology, conscious beings become active participants in cosmic processes rather than passive observers. The search for understanding drives conscious beings to investigate the fundamental laws that govern cosmic behavior, to seek patterns in the apparent chaos of natural phenomena, and to develop mathematical descriptions that capture the essential features of physical processes operating across vast ranges of scale and time. Interconnectedness reveals itself through careful study of cosmic processes. The carbon atoms in living organisms were forged in stellar cores billions of years ago. The calcium in planetary crusts originated in supernova explosions that occurred before our solar system formed. The water that fills terrestrial oceans may have arrived via comets, similar to our hypothetical interstellar visitor. The cosmic web of relationships extends throughout space and time, linking the formation of the first stars to the development of complex chemistry, connecting the deaths of massive stars to the birth of new planetary systems, relating the orbital mechanics of distant galaxies to the local conditions that permit biological evolution. Perspective shifts dramatically depending on the temporal and spatial scales chosen for observation. Individual atomic nuclei experience the collision as a violent disruption lasting nanoseconds. Planetary atmospheres register the effects as temporary enhancements in radiation and particle bombardment lasting days to weeks. Galactic evolution incorporates such events as routine processes contributing to ongoing chemical enrichment. Wonder arises from contemplating the intricate relationships that connect phenomena occurring at vastly different scales. The quantum mechanical properties of atomic nuclei determine the nuclear fusion rates that power stellar evolution. Stellar evolution creates the chemical elements that enable planetary formation and biological chemistry. Biological evolution produces conscious observers capable of understanding these connections. Resilience characterizes cosmic systems at all scales, from individual stars that continue burning steadily despite temporary disturbances, to galaxies that maintain their spiral structures despite ongoing stellar formation and death, to the universe itself that continues expanding and evolving despite local fluctuations and catastrophic events. The dance continues with new participants entering and others departing, but the fundamental patterns persist. New stars form from the debris of old ones, carrying forward the chemical legacy while adding their own contributions. New planets assemble from materials processed through previous cycles of stellar evolution. New opportunities for complexity and organization arise from the ashes of earlier structures. Predictability emerges from statistical analysis of apparently random events, while individual stellar impacts remain impossible to forecast precisely. The overall rates and effects of such events follow mathematical relationships derived from physical principles. The behavior of large populations shows regularities that individual events may not exhibit. Beauty manifests in the mathematical elegance of physical laws, in the spiral patterns of galaxies, in the complex chemical structures that enable biological processes, and in the nested hierarchies of organization that characterize cosmic evolution from subatomic particles to galaxy clusters and beyond. Mystery persists despite centuries of scientific investigation. Dark matter and dark energy remain largely unexplained. The initial conditions that led to our particular universe remain unknown. The ultimate fate of cosmic expansion and the possibility of other universes beyond our observational reach continue to challenge our understanding. The story of our hypothetical collision thus becomes part of a much larger narrative that encompasses the entire history and future evolution of the universe. This single event, violent and brief though it may be, participates in processes that connect the quantum realm to cosmic scales, that link the ancient past to the distant future. Our sun continues its steady journey through galactic space, carrying its retinue of planets through regions of varying density and composition in the interstellar medium. Future encounters with other interstellar wanderers remain inevitable, though their timing and characteristics lie beyond prediction. Each such encounter will add its own chapter to the ongoing story of our stellar system. The solar system maintains its basic configuration despite occasional perturbations from cosmic visitors. Planetary orbits continue their precise mathematical relationships. The delicate conditions that permit liquid water and stable climates on Earth persist through minor variations in solar output and space weather conditions. Life continues its own evolutionary dance, adapting to changing conditions while maintaining the basic processes of metabolism, reproduction, and genetic variation that have sustained biological activity for billions of years. Each species that emerges and eventually becomes extinct contributes to the ongoing development of increasingly complex biological systems. Consciousness expands its understanding of cosmic processes while remaining embedded within the systems it seeks to comprehend. Each generation of conscious observers adds to the accumulated knowledge while confronting new mysteries revealed by improved observational capabilities and theoretical insights. In this eternal dance of matter, energy, space, and time, every event carries significance both as an individual occurrence and as part of larger patterns that connect all phenomena across cosmic history. The collision we have imagined represents one movement in this grand choreography, meaningful in its own right, while also contributing to the magnificent symphony of cosmic evolution that continues to unfold throughout the universe.